Hello, welcome. I have only one announcement. If you have any questions and you want to discuss those questions in person, keep 10-yard distance from me if you want to stay healthy. Now, we kind of started solving this problem, and I think, if I remember correctly, the axis of rotation was chosen at the top end. So all right, I'm going to switch, and probably what I want to do is 731, 322, 731, 322, 731, 322, yep. So now, I still want to finish this problem. It's very similar to the lab situation, to the discussion situation, to homework problems, couple of homework problems. So, the free body diagram, again, let's redraw it. The free body diagram is always the first step to make. This is a ladder, and in this simplified situation, there is no friction acting at the top end of this ladder. So there's only the normal force acting at the top end of the ladder. There is also force of gravity acting on it, and there is the normal force acting from the ground, and this is the force of static friction, which prevents it from sliding away. That's a free body diagram. Step number 2, we have to choose the axis of rotation, that mathematical abstract point. Relative to that point, we have to write torque balance equation eventually. So now let's choose it here at the bottom. Again, in general, it doesn't matter. We can always choose it differently, and we can always add, well, in general, 2 more equations for each component of the net force, which has to be equal to 0. So now we go to the step number 3. For each arrow, for each force, we have to write the torque due to that force about the axis of our choice. And so 1, 2, 3, 4 forces. So we should write 1, 2, 3, 4 torques. The torque number 1, I want to write for the normal force number 2, y. Can't hear you. Because it's 0. Absolutely. And why is it 0? Because there is no lever arm. Lever arm is the shortest distance from the axis of rotation to the line of action. And now, well, for this particular force, the line of action, passes the axis of rotation, there is no lever arm, there is no distance between these and geometrical entities here, a point and a line. And same is true for the torque due to friction. Well, that's a Greek letter tau. I call it T. Every student call it usually T, even it's tau. So it's like a T, but fancy. So. Now, the next on the list is the torque due to force of gravity acting on this ladder. Well, this is the line of action of the force of gravity. Well, a torque has three elements. A sign, we should choose plus or minus, positive or negative. Then force, magnitude of the force, and then something related to the distance, what I call the lever arm, not just me, everybody else. Plus or minus depends on the axis. It doesn't depend on the force. So today's Friday, right? So on Wednesday, when axis was chosen at the top, the torque due to the same force was negative. But now the axis is different, and relative to this axis, well, what do? Well, we kind of bend the line of action towards the axis. And now we can see that this force provides counterclockwise effect, which makes it positive. The force of gravity has magnitude equals mg. And now the lever arm. Could you please tell me the complete definition of the lever arm?
Radius?
No. And first of all, I asked him. But it's a good that you're eager to answer and think about it. But that's not the radius. What is it?
The length relative to where your force is applied.
No. Again, imagine, well, you're not a doctor yet, but you are at the office, and the doctor tells you, well, you have some kind of a disease, you know, I'm not sure what prescription to write. Maybe it's ibuprofen, but maybe, you know, Vicodin, I don't know. So you have to be specific. It's exactly the same kind of reasoning you're using here. You're writing a prescription for the solution of this problem. One deviation from the correct prescription, and that's it. It's not going to work. So first of all, no comments. I tricked you, I guess. I don't know. If you have to press 1, but you press 2 or 3, probably my instructions wasn't clear enough. But anyway, I want to ask a different question now. Erase this. Only 2 options now. Don't press anything. You don't know the question yet. I know the exact definition of the lever arm. No, I don't know. What did you press?
1.
Please tell me the exact definition of what it is.
It's the length of the radius. It's equivalent to r in the formula r times force times cosine theta.
No.
No.
Yeah.
It's
Well, to the line of action, technically. Okay, but good enough. But
It's the shortest distance.
shortest distance, that's exactly right. So the lever arm is the shortest distance from the axis of rotation to the line of action. These 20 words complete the exact definition of the lever arm, and that's a part of the prescription. This procedure is a prescription. So let's see. Well, actually much better than it was last year. So, but now we're all on the same page. So the lever arm is the shortest distance from a point to a line. Which point? Axis. Which line? Line of action. That's it. But we can't use this definition until we actually see this line. Yeah. So we now have to draw it. This is the axis. This is the axis. This is the line. So the shortest distance means it has to be perpendicular to the line of action. Well, and let's actually make it green. So this, nobody wanna work on Friday, even the system. This green segment represents the lever arm of the force of gravity acting on the ladder relative to the axis of rotation chosen at the bottom end of the ladder. So now we see it. And now the next part of the reasoning is, well, how can we find it geometrically? Yeah, so we have a right angle triangle, and well, this is the right angle triangle. That's the lever arm of the force of gravity, 90 degrees. This angle is 30 degrees, and well, this line represents the hypotenuse of this triangle. If the whole ladder is 2 meters long, this hypotenuse will be equal to 1 meter. Any questions on that? Center of mass breaks it into equal halves. So now we can write the expression or the number, well, the expression for the lever arm. It has to be equal to, I want to write the expression, a half of the length of the ladder times a certain function, sine or cosine? Sine. Because the lever arm, yeah, this one, is opposite to the 30-degree angle, so sine of 30. And finally, we should write the last torque. The normal force at the top is acting on the ladder along this line. The line of action is a horizontal line, points to the right. And what does it make it? Positive or negative torque? Negative. That's the first part of the torque, first part of the reasoning about the torque. Now, magnitude, well, we use a standard agreement now. I don't show vertical bars to express the fact that it's a magnitude. I just know that's the magnitude. Times the lever arm. Now we have to apply the exact definition of the lever arm. And what I want everybody to do is actually calculate it. So I'm going to give you a set of answers to choose from. The lever arm equals 2 meters. 2 meters times sine of 30. 2 meters times cosine of 30. 2 meters 2 meters times tangent of 30. 5, 6, 7, 8. 2 meters divided by sine of 30. 2 meters divided by cosine of 30. 2 meters divided by tangent of 30. 1 meter. 1/2 of a meter. Something else. And of course, you can't choose your answer without actually seeing the lever arm in your picture. So you have to draw that picture. You have to, well, what do you have to do? You have to take your pen or pencil, then you have to place it at the location of the axis, and then without taking it off that piece of paper, you have to draw a line towards the line of action. Make sure that this line is perpendicular to the line of action. And as a result, what you get, that's the lever arm. Then you should look at it, find a right angle triangle, use that triangle to well, calculate the length of that lever arm to relate it to known values like the length of the ladder, for example. You know, the length of the ladder is equal to 2 meters. So if still not sure, well, check your good luck, press anything, and see how it works. Don't forget also there is a sign-in sheet floating around. We have two competing answers, number 2 and number 3. Well, first of all, it's a very good thing that almost nobody had chosen 2 meters, because clearly the ladder doesn't represent the lever arm. Again, this is what we have to do. See, look at me. This is axis. So I place it here, and I draw, oops. Again, and I draw a line to the line of action. What's wrong with this line? Not perpendicular, wrong. So what do? Try again. If you didn't succeed first time, try and try again, but try something new. Otherwise, it would have been insane. According to Albert Einstein, who is very smart, well, was. So we have to draw a line like this at 90 degrees. That's it. That's the lever arm. The lever arm for the force, normal force number 1. And now, of course, we should find that triangle we want to use. In this triangle, what do we know? We know the hypotenuse, which is equal to 2 meters, and we know, well, any angle. This is 60 degrees, and this is 30 degrees. So the lever arm is adjacent to the hypotenuse, so we have to use this. And so again, the length times cosine. And we're finally done with the step number 3. Oops, 3. So after we're done with the step number 3, what do? Step number 4. And the step number 4, well, I want to keep it, I don't want to clean it up. So the step number 4 is actually writing the torque balance equation So 0 plus 0 plus plus mg times a half of a length times, what was it, sine of 30, and plus negative torque, normal force number 1, times the total length, times cosine of 30. We just put them all together. We just have to make the whole thing to be equal to 0. Well, in this equation, we know everything but one variable. So this is 10 kilograms, 10 meters per second squared, 2 meters over 2, sine of 30, which is a half, negative, that's the normal force number 1, 2 meters, cosine of 30, which is 0.87, equals 0. So you can calculate the normal force immediately. Well, that's not what we want to calculate, but in this situation, actually, this number automatically gives the answer, because we have only 2 horizontal forces acting on this ladder. Only 2. Normal force to the right and static friction to the left, which means these 2 forces must cancel each other. That's basically force balance equation, which means the force of static friction we are looking for will be equal to the magnitude of the normal force, which being given by this equation. Any questions? There is one additional question I added just before the lecture. What should be the minimum value of the coefficient of static friction in order for this ladder to be still, to be at rest? Well, again, remember, the force of static friction can have any value between 0 and the maximum. So the force of static friction should be less or equal to the coefficient of static friction times the normal force. Which one? Well, this one. And in this problem, we have only 2 vertical forces. The force of gravity acting on the ladder points down, and the normal force at the bottom points up. So these 2 forces also have to cancel each other out. That's, again, force balance equation relative to the y-axis. So we can rewrite this. Force of static friction should be less or greater times mg, which gives the answer. Because, well, you can calculate this number, and you know m, and you know g, and you know g. So this calculation tells us that the coefficient of static friction cannot be less than this ratio. If it's less, it slides away. That's it. You just can't. To prevent it from sliding away, in that case, you should choose a different angle. Make it steeper. Basically, that's it. But if your coefficient of static friction greater than this, it means, well, you can add some mass. For example, you can step on the ladder, and still it will be at rest. Any questions? So that was the last actual problem. I just want to mention a couple of things. Like this, one of the applications of this theory. medical application. If you know, people say, don't lift with your back, lift with your legs. There's an explanation for that, pure physics. So the average person, let's say the mass of 60 kilograms, and if that person lifting a weight by using the spine, so you can make a rough estimation for the magnitude of the force acting on all vertebrae. You just have to apply the torque balance equation, and turns out the force of tension provided by the muscles, well, thousands of newtons. So if you try to do it like this, and people know that, yeah, that's why they say, use your legs, not your back. Another important application is analyzing stability of systems. Let's imagine this is a building, a tower. It's in equilibrium. Is this equilibrium stable? Well, let's see. If I deflect it from equilibrium and I let it go, it comes back. That's a stable equilibrium. But of course, if my angle becomes larger and larger, at a certain point, it falls. So, there is a building like that in Italy. Yeah, what's the name for this? Yeah, it's in Pisa. What's wrong with this? Well, the center of gravity is over here. Force of gravity acts like that. And if the force of gravity generates torque, which brings it back, that's a stable equilibrium. But if the force of gravity generates torque, which moves it away, that's unstable equilibrium. So it's just too tall. So for this situation, the force of gravity applied to the center of mass points within this area. So the torque due to gravity actually makes it stable. But if I add some extra mass, the center of mass shifts up, and now the line of action of the gravity missing the base. So now this torque makes it rotate, well, clockwise, and it falls. Well, American Eagle. It is a toy. But is it a stable equilibrium? Yes. Why? Very simple. It has some extra mass in the end of the wings. So the total force of gravity acting on this, actually, the center of mass is here at the beak of this, right? So the force of gravity points down, the normal force from my finger points up, net force is 0. But what about torque? So we can imagine in our mind that there is this bird divided in two halves. So there is a force of gravity acting on this half, and there is a force of gravity acting on that half. So we have two torques, and it turns out they also balance out each other. You don't have to play with the bird. You actually can make a thing like that at home. You just need some wire, wood, pretty stable equilibrium. It's just easier to see. You can see two different parts of this. Yeah. Mass number 1, mass number 2. This torque is canceled by that torque. The force of gravity, the actual total force of gravity, passes the axis of rotation. So we can use this fact now backwards for measuring the location of a center of mass of a complicated object. Center of mass, we know how to calculate it in general. It's very simple. If you have a rod, the object number 1, the object number 2, the rod itself, that's a pretty simple system. We can replace the rod with a small ball located at the center of mass of the rod, and we can calculate the location of the center of mass, and of course it's going to be in the middle because of the symmetry. But what if the system is not symmetrical anymore? The center of mass of the system now is not here. Where is it? Well, of course, it shifts closer to the heavy part. Actually, I can find it. How? Well, I just need to find that place which provides a stable equilibrium for the system. How do I know it's supposed to be the center of mass of the whole system? Because the force of gravity has to be applied to the center of mass. And if I move my fingers away, the force of gravity still is applied to the center of mass. But now, the torque acting on the system is not zero. So this can't be center of mass. This point can't be center of mass. Only that point where the net torque becomes zero, that point is the center of mass. That's how can I measure it? And even if we have very complicated objects, we can measure center of mass. Measure. Well, of course, we can calculate, but measure is easier. We just need the plumb bob. So that's what I have to do first time. You see this line? This line represents many, many points where center of mass should lie on. I don't know yet, this point, or that point. So what can I do? I can suspend the same object. And now I have another line. So all I have to do is take a piece of chalk, draw two lines, and the point of intersection shows the center of mass. It doesn't have to be inside. Yeah. The center of mass is an abstract point. It doesn't have to be inside an actual object. It's just a point in a space. But if I had it found for a solid object like that, okay, you should help me. The line number 1. I'll be back. The line number 1. I need more hands. The line number 2. That's center of mass. Let's check. Well, strings kind of mess it up a little, but well, more or less. Come on. Close your eyes, okay? While you're watching, it doesn't want to work. So if you ever need to find a center of mass, all you need is a plumb bob. People knew that thousands of years ago without knowing why it works. Well, this is an example of my situation number 1 with the rod. This is situation number 2. And finally, we are done with this topic. And we start from a question. That's not a new question, that's a review. A disk. Okay, this is done, this is done, this is done. So we give it a spin, and it's slowing down. That's it, that's what is happening. And the key word is slowing, yeah, slowing down. When object is speeding up, velocity and acceleration are parallel, but when an object is slowing down, the velocity and acceleration are opposite. It works for any kind of a motion, including the rotational motion. If the velocity, angular velocity, is counterclockwise, but the object is slowing down, opposite means clockwise. So the angular acceleration, alpha, points clockwise, as you said. And for any, we've seen this slide before, for any rotational motion, basically, it's a combination of many circular motions. Yeah? Each individual part of this fan makes a circular motion, and for each individual part of this fan, we can apply the Newton's second law. Again, we saw this slide before, but that slide described the motion of only a single, remember, a single like puck. Yeah. But now we just have to make a step ahead. If we have a solid object, we can write the same equation for each part of it. What do we have to do next? Well, as we know, the tangential acceleration depends on the radius. But for the motion, for rotational motion, all parts of this fan have exactly the same angular velocity. All parts of this fan have exactly the same angular acceleration. So if we rewrite the Newton's law, making a transition from linear variables to rotational variables, that will make mathematics much easier for us. So instead of using the tangential acceleration, we can use the angular acceleration. That's how they related. So we just replace the tangential acceleration with angular times radius. And as we know, when we talk about rotational motion, the force is not very important. The torque, which is force times distance, is important. So we take this, multiply everything by a radius. This represents the torque. Here we have a combination mass of that individual particle, and the distance from this individual particle to the center of, well, of that circle it makes, to the axis of rotation of the whole body. And we can write the same equation for all particles an object is made of, for all of them. And then we can add them up all together. So if we're adding torques acting on all particles, the result is what we call the net torque. And turns out the net torque has to be related, directly related to the angular acceleration. This parameter, this variable, angular acceleration, is the same for all parts of an object, for all small individual parts of this fan. But this coefficient between the net torque and angular acceleration has a kind of complicated structure. It's not just a mass anymore, like for Newton's second law. It's a mass times distance squared, which different for different parts of that object, and we should add them up all together. So as a result, we come up with a new physical quantity and a new physical law. So this variable, this is a coefficient between a net torque acting on an object and the angular acceleration of that object, has a name, well, two names. Some people call it rotational inertia, like a mass is a translational inertia, so rotational inertia, but that's kind of outdated. The contemporary term is a moment of inertia. Rotational inertia, the moment of inertia, inertia. If it's a very large number, it's very hard to spin an object. It's a very low, small number, it's much easier to spin an object. That's it. Now, the structure of this variable, mathematically kind of complicated. You see, this Greek variable represents the sum. The sum of all those products. We don't have to do that because it has been done for us. We just have to use final results of that kind of a calculation. So here, if we have a long rod with nothing else attached to it, the moment of inertia of this rod relative to the axis traveling through the center of mass is equal to 1/12 times the mass of this rod times the length of this rod. Done. Why? Who cares? A sphere, a ball. If you have to calculate the moment of inertia of a sphere relative to the axis traveling through the center, that's your equation. A cylinder, something like this. Well, a word cylinder is ambiguous because people call this thing a cylinder. So, but normally we would call it a hollow cylinder, or if we just look at the rim of it, we call it a ring. And if we just say a cylinder, that's what we mean. For this object, the moment of inertia relative to the axis, which is perpendicular to the face, and travels through the center point. So imagine this is the axis. It should go like this. Relative to this axis, the moment of inertia equals to 1/2 times the mass of it times the radius squared. So from now on, all we need to know is just what object being used. If it's a sphere, that number. If it's a cylinder, this number. If it's a hollow cylinder, what do you think? In the middle. And for the hollow cylinder, the radius of the cylinder. And if we look at this like this, for the hollow cylinder, that would be just mr squared. Because basically, we just have many, many points, but they all at the same distance. So when we add it up, the distance is the same. And all we need to do just to add up all small masses, and that gives the total mass of the cylinder. So hollow cylinder. Now, remember, all these equations only work when the axis of rotation goes through, well, the center of mass. And for the cylinder, it has to be perpendicular to the face. For the hollow cylinder, also has to be perpendicular to the, well, circle. In general, we could have spin it differently. I can drill 2 holes, and I can spin it like this. The equation stays, but the number, the rotational inertia, would have been different. not this anymore. What do you do if by any reason you need it? What do you do? Google. They all have been calculated for any possible axis, for any possible shapes. And this is an example. What do we do if we have a combination of shapes? For a single point circulating, the moment of inertia is equal to the mass of it times the radius of a circle. For a rod, the moment of inertia is equal to, well, 1/12 length mass. But what if we put them together? Well, the rule says, or a disk, doesn't matter. The total rotational inertia is equal to inertia of the first object plus inertia of the second object, like the mass. That's it. So for the system like that, if you want to calculate the moment of inertia relative to this axis, it has to be equal to 1/12 ml squared for the rod plus this mass times distance squared, which distance from this mass to the axis. If instead of, well, in this situation, instead of a rod, you're having a disk, well, what do we do? The total inertia of this system should be equal to, well, 1/2 times the mass of the disk, 0.2 kilograms, times the radius of the disk, 20 centimeters, which is 0.2 of a meter squared. That's this, plus for this single tiny ball, the rotational inertia equals this. So the mass of this ball is 50 grams, which is 0.05 times what's the distance from the axis of rotation to the ball? This distance r still equals the radius of this disk, so still 0.2 squared. What is the unit of the moment of inertia? A kilogram times a meter squared. That's it. It has no special notation. It has no special name. So calculation gives you something, kilogram a meter squared. And, well, now you know everything about an object which makes rotational motion because of the torques acting on it. You only have to apply this law directly to the system. What is the net torque equal to? The sum of all individual torques. And it has to be equal to this product. And you're going to do in the lab. In the lab, you will be measuring angular acceleration and calculating torque and using that work for calculating the rotational inertia of a disk. And then you will compare with the number which you can get calculating it directly. And of course, you have a couple of homework problems to do. Every time you have to remember, well, that's what we call the Newton's second law for rotational motion. You just have to apply the Newton's second law for rotational motion for an object which is moving in a circle. But if you have a system you know what to do. This is basically a review question from now on. So I sent, no, here, my last slide. Oops. On Monday we have a review session. You have to prepare your questions. Where is it? Here.
I think there's a problem with my clicker, because every time I press something, it just. Oh, you changed the channel? Because it used to be 21, right?
I changed the channel last time.
I wasn't here last time.
Well, now I know.
Okay, I see. Good to know.
Let me check if it works now.
Okay. Cool.
Yes, it does.
Thank you so much. Sorry.
Can I send you a picture of this?
Did you finish your work? Did you calculate it and did you try it?
I will. Can I send you the picture of it after?
Yes, you can. How many trials do you have left?
5.
Oh, okay. Go ahead, try it. And if it doesn't work, send it to me. Yes. I don't know. I left it, and yes. Have you sent me an email? Someone sent me an email with exactly the same question, housing appointment and stuff. It wasn't you. No? Send me an email. Yeah, fastest way. You can attend a different section, but you should tell me which would work for you. Someone was hogging the sign-in sheet. Otherwise, the line would be much shorter. Proportionally to the homework problem. More problems on homework means more problems on the exam related to that topic. Less problems on homework, less problems on the exam. Well, best case scenario. I emailed to you.
I was wondering if we could, I don't know, anything that's possible I could do.
At this point, it's practically impossible. The homework number 1 has been closed. You didn't even start it.
I started parts of it, I think. That's the issue.
No. At least according to my system.
I remember starting parts of it and then the last bit.
Well, you did some exercises which, thank you very much, which were like a math pretest. I saw some course concept again for it. Definitely started, but the actual homework assignment 1
So I remember I didn't finish them, so
so that has been closed.
is there, I mean, is there any way possible, because I mean, I understand that it's closed and everything, but it's just because I've just been all over the place at the moment, and
That's I don't understand. If you had any issues, health, something family related, something else, first of all, you have to notify your instructor. You know, general rule has nothing to do to physics or to me. There are general rules which apply to every student.
I understand.
And I can't bend any rules by any reasons. If you have any official reason, it has to be documented in certain way. Only after that, I could act. Right now, you have probably, I don't remember, a week to finish the second homework, because that will be closed only, I think, on the day of the exam. So that's one option. If you do that, you're not losing these points at least. If you're losing points for the homework number 2 as well, in that case, you're crossing the boundary, because, again, there's a rule, general rule, which says in order to be graduated from the course, every student should have at least 50% of the homework done. Still, I'm New York, and if there is again a reason for an extension, I can make an extension. I can give an extension, but it has to be an official reason, like health or something else. Like if you just spend your time on something else, I can't